Good morning.
Yeah, so let me just share the screen. Okay, so let's get started. So in the previous class, what we were looking at was the perceptron, and we saw a way in which you could learn the perceptron algorithm, where you could learn the perceptron. So it essentially boiled down to learning these weights. So these W's, that's what you wanted to learn with some data. And the model of the perceptron was something like this. If you have a hyperplane, and what you're essentially trying to learn is the hyperplane. So if you have on one side you have the positive examples, and on the other side you have the negative examples. So this was the underlying model. So it was a linear model, okay, because the decision surface was a linear surface. It was like a linear boundary, and this is what you were trying to learn. Okay. So we saw an algorithm for it, and we said that it converges provided the underlying data that you have is actually linearly separable, meaning that there is a hyperplane which separates the two classes. Okay, and we also saw that there is an underlying loss function. So actually the perceptron algorithm is an optimization algorithm. It's actually solving this optimization problem to optimality. So the underlying method that is used is actually what is called the stochastic gradient descent. So you will see this later in the probably in the next semester, and also when you do machine learning and if you're taking the optimization elective. So this is a class of algorithms called stochastic gradient for solving the optimization problem. Okay, and we also saw, you can, instead of using just x, the features x, you can transform it to some higher dimensions and then try to use a vector w in that higher dimension. Okay, so that's also something we saw. And where we left off last time, what I told you was, the perceptron, you can depict it in this kind of, using this kind of a graphical way. So where there are these features, there are these weights which are tied to each of these features. You compute a linear function, and then there is some kind of a threshold that you apply. So you see if sigma wi xi, if this is greater than or equal to 0 or not. And so depending on that, the function, ultimate function that you have is this kind of a threshold, where if the summation wixi is greater than 0, you consider it as +1, and if it's less than 0, you take it as -1. So this is what the perceptron was trying to do. Now there are different versions of the perceptron, or I would say relatives of the perceptron, depending on some tweak in some of these aspects. For example, so we won't go into an in-depth study of all these relatives. You'll see this in more detail in machine learning. But one thing to see is that what did we do? We had this kind of a hyperplane. Now, is this hyperplane unique? If you have these two sets of points, do you think there is a unique hyperplane which separates them? Can there be multiple W's which still divide into one part into the positive class and the other part into the negative? What do you think?
There can be multiple.
There can be, right? So you can have something like maybe even this. This is also a valid hyperplane, and maybe you will get another vector. So something like, okay, so this, my drawing is bad. So, but you'll get maybe a different W. Yes, there are different such W's. Now, what is the W which kind of, something like this, which goes directly in between all the points? Okay, in some sense, like it's what is the mid hyperplane? Okay, so if you want to find that, how would you go about? So that's what the SVM does. So SVM is one such thing which tries to find the best hyperplane. Okay, so the best hyperplane in the sense of more a central hyperplane. Okay, in that sense. So SVM is another classifying algorithm. So this is support vector machines. So there is a way to actually formally write down the problem in terms of an optimization problem and solving it. Okay, so that is support vector machine. Now, so this is one, another algorithm, another classifier. So it's a different model actually. Okay. Now, so that was SVM, and now also depending on the kind of thresholding that you use. For example, here it was a hard classifier in some sense. So perceptron was a hard classifier in the sense that you always got a +1 or a -1. So either +1 or -1 was what you got. It gave you a +1 or a -1 for each instance. Now, instead of this, like, for some points which are very close to the boundary, right? So something like somewhere here, if you have a negative point, so you don't want to be like, very conservative that way, saying that it's a negative point. You want to have some notion of probabilities here. Okay, so in the probabilistic sense, if you want, what can you do, right? Instead of giving a hard threshold here, is there some other function which you can use to smoothen things out? Okay, so that would give you what is called the logistic regression classifier. Okay, so we will see an some aspect of logistic regression in terms of what is the function that you can use to smooth this out today, because that function is also going to get used in neural networks. Okay, so let me just talk of the softening aspect. So suppose, okay, so this threshold function was something like this, right? So what we had in perceptron was, essentially you had a function like this. So this was like +1 if x is greater than 0, and -1 if x is less than 0. Okay, so if x is less than 0, you had -1. Okay, so of course you had a w transpose x. That's what you finally substituted. But generally the function, the thresholding function, it's also called a step function. Okay, so step function or a threshold function is something like this. Okay, now if you instead wanted, instead of having a value like this, so this was +1 and this was -1. Instead of this, suppose you wanted some function like this, which is a little more smoother. Instead of going all the way like this, maybe something like this. It is still in the range of -1 to +1, or maybe like if you want probabilities, you want it like between 0 and 1, right? So something like this. Suppose you had some such function. Okay, so what would you use, right? So that brings me to what are called the sigmoid functions. So a sigmoid function is just represented in this way. It's written like this: sigma of x. Okay, so if for any input x, so this is a number, so this is an element of R. So what sigma of x gives you is this function 1 by 1 plus exponential e power minus x. Okay, so this is e power minus x. Okay, so so let us see what happens. So if x is, what happens if x is 0? So if x is 0, what will be sigma of x?
0.5.
0.5.
0.5, right? So this part will give you a 1, and so you get a 0.5. Now, so that is something like this. At 0, you have a 0.5. Okay, and suppose x is a large positive value. So it's like a very big positive value. So what happens here? E power minus x becomes what?
0.
Yeah,
Close.
yeah. This becomes close to 0. And what you get for sigma fx is going to be 1, right? So this will be close to 1. Okay. And what happens if x is like a very negative quantity, a very like large negative? So in the sense, in this part, somewhere in the tail end. So what happens there? What happens to e power minus x there?
Very
It will
large.
tend to infinity.
It will tend to infinity, right? So e power minus x will go towards infinity. And so what you'll get is sigma x goes to, it goes towards 0. Okay, so that's where you get this kind of a function, right? And so this has an intuition of probabilities. So sigma of x will always lie between 0 and 1. Okay, so that's why it has an intuition of probabilities, and this is popularly used in logistic regression. Okay, so yeah, so now this sigmoid function is also useful in the neural networks that we're going to see today. So the neural network is basically a way in which you compose many of these perceptrons. Okay, and the idea is we saw like linear classifiers may not always be the best. Okay, so it may not be very powerful. Of course, you can do some things by using these functions phi, in some cases. But more generally, it is good to have something like a nonlinear classifier to build nonlinear functions, and the neural network gives you one way to do that. So it's actually a multi-layer perceptron. So in the sense, what you can do is you can have something like this. So we're just going into neural networks. So what we had was x1 to xd. So these were the features. Now, in the perceptron, we had a single weight vector, which gave something like a sum. So let me just write it a little big. Okay, so I'm just writing it big for a reason. So what we had was, these were W1s up to WDs, and we computed, first we computed a summation Wi xi, okay, and then there was a step function that we applied to it, right? So then there was a threshold, so some function h that you applied. Okay, so h of w transpose x, and of course there was a bias that you could add, so w transpose x plus b. So this is what you did in perceptron. Now what you can do is you can also have multiple such components. So you can have, this is one weight vector. Now you can also have another weight vector, right? So something like this, another set of weights. Okay, so maybe let me call it what do I call it? So let me say this is W11 and this is WD1, and maybe I can call this W12 all the way up to WD2. Okay. So here what I can do is, again I can get, and I can have one more value B here. Okay, and I can get something like this WIXI. So so let me just write it in full. So W12X1 plus W, what's the next one? So if this is X2, you'll get W22. So something which leads here, right? So W22X2 plus so on, plus WD2 XD. Okay, so that would be this part, and then you could again apply an h of that, right? So you can have different kind of weight vectors. For example, if you wanted to learn a multi-class classifier, so what we saw in perceptron was like binary, but in general what you could have is, for multi-class perceptron, so in multi-class, what you could have is you could have a W for each class. So W K, okay, so WK for class K. Okay, and then what your model would be something like this. So Y is your prediction is you look at whatever is the max, R max, whichever gives you the maximum value of W, whichever W gives the maximum value, that is what you consider as your class. Instead of taking greater than 0 or less than 0, this is also another way people do a multi-class classifier. Okay, so that is like having multiple such units. Now again, you can have okay, so this can go on and on, and finally you can have one more layer, right? You can just, in general, you can apply any function h here for these intermediate steps, and you can have one more layer like this, right? And another set of weights, and so on and so forth. So you can keep on doing this, and finally there is some kind of an output that you want to get. Okay, and maybe if it's a classifier, so if there are k classes, so maybe this is the final thing that you want. So maybe a y1 to yk, that is what you finally want to predict. Okay, so your model can apply this in a, how do we say it? It's a composition of many such perceptrons you could do. Okay, so that's exactly what a neural network is. Okay, so I maybe my drawing is, it may not be the best. So let me just see if I can show you something. So this is actually a famous book on neural networks and deep learning. So I'll share the link with you. So something like this, right? Right, so you have a layer. So this is your input features, the first part, and then you can have another set of intermediate steps. Okay, intermediate perceptrons in some sense. They're also called neurons, and finally you can get an output. Okay, so this is actually what a neural network is. Okay, so so the important thing is this function h, right? That has to be, it cannot be linear, because then you will again learn a linear classifier. So maybe let's just take a small example. So maybe suppose you have two features, x1 and x2. Okay, and what I'm going to do is I have the first set of maybe like three parts here. Okay, so I have these weights, so w1 1x1, and maybe this is w1 2x2, so w1 2, that's it, in x1 here, so w1 2, and there is this part which has a weight of w1 3. Okay, and similarly, so what I do is I wij means I'm connecting uh, it's a connection from I to j in the next layer. Okay, the next layer. Okay, so these things will get, I mean, I'll formalize it a little more. Right now, I'm just writing it in a very informal way. So maybe something like this. Now, W, so this would be like W21. Okay, and this can be like W22. Okay, and this is like W23. Okay, and so, what I do is, there are two parts here. So here there is a, W, whatever we saw, right? So W, so this is the first neuron, this is the second. So these are also called neurons. These units are called neurons. So the three neurons here, and so this is something like this, WJ1 XJ, okay, plus there is B1 here. Okay, and so that is one part, and there is a function that you apply. Okay, now right, so if this h is just the identity, if it's just the linear function, what you're going to get is you're going to get back this form, which is again the linear form. There is no non-linearity that gets added. So you can also check it, like if you have one more layer here. Okay, so more generally, what you're going to have is this is corresponding to the first layer. Okay, so I'll just write it like this. This is the first layer of weights. Okay, so all these are in the first layer. Okay, now similarly, what you can have is a layer 2. So this is a second layer. So this is the first layer. There are three units here. Okay, so there are three units in layer 1, and maybe in layer 2 you have just two units. So this is unit 1 and this is unit 2. Okay, so yeah, so what I will write is z. So this part, right, on this left half, whatever value you get, I'm going to write it as a value z. Okay, so I will write this as say zil. Okay, so this is just going to be what, so this is the layer, L is the layer, and I is the particular neuron. Okay, I is the neuron or the unit. Okay? So these, these kind of blocks, right, or these circles that we write here, these are also referred to as neurons. The name is kind of inspired from biological networks, those biological neurons, where there's some input coming in and there is some activity going on and an output comes out. Okay, so it's just as simple as that. But these are referred to as neurons. Okay. So ZIL is actually the value that you get when you take each of the previous layers, whatever is there in the previous layer. So something like W J. So J is basically all these values, what you had in the previous layer. So W J I, right? So it goes to from maybe X1 to this layer 1. Okay, so that is WJI and XJ. Okay, and so this product, this product, and you sum it up over all the previous layers, whatever is in the previous layer, plus a value BJ, sorry, BI, right? So BI for each neuron. So this is B1. So this is B11. Okay. Okay, so this is one value that you get. And finally, there is another value A. So I will represent this as AIL. So this is actually the notation comes from what is called activation. So this is the final value. So this is an intermediate value that comes in. Then there is an additional function that gets applied. So that is called the activation function. Okay, and what you get is AIL. The result is AIL. So this is basically a function applied to the ZIL. Okay, so that is what you get. So the output of this is AIL. Okay, so this will be A1, 1, and the output of this will be A2, 2. and the output of this will be A32. So third unit in the second, sorry, in the first layer, right? We're still at the first layer. Okay. Okay, see, the notations may be a little cumbersome, like when you just look at it, but what is important is you understand what is going on internally, right? Why are we doing this? It just, there's some logical sense of, connections between one layer to the next, and what these, which layer these weights correspond to. That's why there are these multiple indices. Okay, so I want you to stop me if there is any doubt. Okay, otherwise we'll not understand. You'll not be able to understand when we go forward. Okay, so these are the different parts, and more generally, so this is in layer one. This is what we had. Okay, so these are whatever the neurons that were there in layer one. Now, if you had to look at layer two, okay, so this is another layer that you have of neurons. And here there are two units. So here I will write these weights as W. So this is layer one, and from layer one, the first neuron, to layer two, first neuron. So this is W11. And it corresponds to the second layer. Whatever you're going to get is for the second layer. So that's where I write it as W11 with a superscript 2. Now, similarly, this will be, can you tell me what this will be?
W12 of 2.
Yeah, W12 of 2. Okay. And so this is again, what is this?
W21 of 2.
Yeah. So W21 of 2. And this is again W22 of 2. Okay. And this, so like that. Okay. So this, let me just write one more here. So this is W32 of 2. Okay, so generally Wij of L is the weight for neuron I. So this is the weight of neuron I in layer L minus 1 to neuron J in layer L. Okay, so in the layer L. So that's what this denotes. And so what do you get in the layer 2? Let's just try to write the outputs, right? So what is going to be Z 1, 2? Can you tell me? So now what you have to use is the output from the previous layer. So actually here it's just going to be AJ. So AJ L minus 1. Okay, whatever comes out from the previous layer, that you're going to use, you're going to multiply it with the weights and compose it together to bring in the next unit. So again, here you'll have there's going to be a Z12, okay, and there is an A12, okay. So similarly here, you're going to have a Z22 and A22, okay. So can we just write down what these values would be?
So it will be W11 of 2 into
Yes.
A1 of 1
A1 of 1. So this value W112 into the output of this unit. So that's A11, correct?
plus W21 of 2,
W21 of 2.
A2 of 1.
Yeah, times this one, right? So A2 of 1.
Yes.
Okay.
Plus
And you can also have this is called a bias term. So this will be B1, 2. Okay, so plus B1, 2. Okay, so this is Z12, and you can also have its activation. So A12, finally what comes out here is some function that you apply on Z. Okay, so something like this H of Z12. Okay, so remember again, yeah. So if you try to now, let's just try to expand it a bit more in terms of the previous layers. Okay, so Z12 was this. So if you try to write it in terms of A11, so what did we get? So Z12 was W112 and A11. So that is actually this value, A11. So that was again, what did we write it as? You had
It's of
Z11.
Z11.
Experiment.
Yes.
Then we need
Yes.
to consider A13 also, na?
Which one here?
In the Z 1 of 2,
Ha ha ha. Yes, yes.
A13.
So yeah, so I needed to draw this connection. So yes. So there's one more here. So that's right. So you have W31. Can you help me finish this?
W31 of 2 into
2.
A3 of
Yes.
1.
A3 of 1. Okay, so you can configure this network in different ways. So sometimes the most general network is where you have connection between every set of neurons from one layer to the next. Okay, but sometimes like this is something that people explore with. They try to see if one connection is not there, a couple of connections are not there, what happens. Okay, but yeah, the general framework allows for all connections. All right, so let's just try to expand one more layer. So Z12 was what we wrote in this manner. Now, if you try to plug in A11, so which is the output from this neuron, okay, so this one in red. If you try to plug in that, what would it give you? Can you just tell me? So let's just write A11 once, maybe. That might make things a little bit clearer. So A11 is what?
H of
H of, so this H of Z11, right? So this is one thing. So what is Z11?
W11 of 1 into x1
Yeah, W11 of 1 times X1.
plus W21 of 1 2 of 1 times x2.
So we are computing this one. So yeah, W. So it's actually as per the way we've written, I think it's W21,
Yes,
right?
W21, sorry.
Yes. So W21 of 1 times X2 plus
Plus
so. Okay,
bias.
so yeah, plus a bias of B11. Okay. So now if you plug this back in, so this A11 is what we wrote here. Okay, so suppose H was just the identity function. So suppose if H was just Z11, okay, you're not going to apply this function, you're just going to take the value of Z as it is. What you will get here is again W111 of X1 plus W211 of X2 plus so on plus B11. Okay. So like that, this will go on. So in case you didn't have this H function, if it was just the linear function that you're going to take. Now what's going to happen is ultimately even this Z1 is going to give you again a linear function. So this is going to be linear in x1 to xn. Okay, so x1 to xd. Okay, and similarly so now if you again apply a linear function here h, okay, so if you are not going to have this h, you're just going to output whatever z12 gave you, again you'll get a linear function. Okay, so in that sense, this h function, it's very important that you plug something here to get in a non-linear element. Otherwise the final result that you're going to get is also going to be linear. So this is going to continue on and on, and finally you're going to get some value. So if there are L layers, so suppose there are so this was layer L. Okay, so layer L, and finally there was a last layer. That is what is called the output layer. Okay, so this is called the output layer. And here the values would be something like this, A1, L plus 1, all the way up to how many ever layers you have. So maybe if you have 10 layers, something like this. I mean, if you have 10 neurons in the last layer, you'll get something like this, A10, L plus 1. Okay, but what is going to happen is if you didn't have these H, whatever you got in the result, that is also going to be linear. Okay, and typically what's going to happen is if this is a classification problem that you're trying to write a neural network for, this number will be as many as a number of classes, and this is what you will observe. Your training data will give you these values, and that's why this is called the output layer. Okay, so this is the reason why you need to choose some nonlinear function h. Okay, just having a linear function will not work. So you need some nonlinear functions h if you want to get some more power for your neural network. Okay, you need some nonlinear activation functions. Okay, now there are many possibilities here. Okay, so nothing prevents you from using any function. You could use anything in principle. Some of the most popular neural networks, some of the most popular applications make use of the sigmoid function here. Okay, so H is actually an example is sigmoid function, so which we just wrote it, right? So we wrote this as 1 by 1 plus e power minus x. Now, another example people use is what is called the tan h function. So it's just tan h, the hyperbolic function. So tan h of x. Okay. So this is one example that people use. There are several such ones. Then there's another one called the ReLU. Okay, so this is something which is just max of x and 0. Okay, so it is something like this, right? So you have x here, and for all the negative values, you're going to get 0. And the moment x becomes positive, you're going to get that value itself. So it has a shape like this. Okay, so this is also one thing that people use. Okay, so more generally, so this is I don't know if you're able to see my screen, I mean the various plots. There are a whole array of activation functions that people use. Okay, so there's this linear function, of course, which is there. Then there is this ReLU. Then this is a sigmoid function, the tan h, and step function we already saw. That's the threshold function, and so on. Okay, so there are different possibilities you can use, and people typically try to explore different sets of functions and what is the best. Okay, so ReLU is something, somehow it's now quite popularly used. So this is called rectified linear unit. Okay, so these are just jargons, I would say. Finally, it comes down to trying out different functions and using whatever works. Okay, so I just want to pause here for a minute and just find out if people are okay with whatever has been taught so far. I know there's suddenly a lot of notations which are coming in, but these are things that I don't want you to mug any of these notations. This is something that you can try to write logically, whatever makes sense, because mugging it's not going to get us anywhere here. Okay. So are there any questions? Is this clear? What is happening here and all that? Rishabh, is this
Excuse
clear?
me, ma'am. No,
Yes, tell
ma'am.
me.
I mean,
Uh,
please go in the slide.
yes.
Ma'am, I want to know that these x1, x2, x3 are the data point, na? It is not a feature. It is a vector. And in the first layer, what we are getting means uh, for every data points, we defined different weights
Mm-hmm.
for the each layer. One point means I want to say that the place where you use the red color.
This one.
Yes, ma'am. Means
Okay.
for each point we will have the different weights for every different vectors.
So
Training purpose.
okay. So actually, what happens is, these x1, x2, these will serve as, this is an input layer. Okay. So this is like your features, whatever you have in your training data. These, your features will come in this part. This is the very, like, this is like layer 0, you can say. Okay, and so this you would, I mean, so this is actually x1. Do we write it as x1? This is actually the value of a1 0, and this is a2 in the 0th layer. Okay, so that's how it goes. Okay, and now what we are trying to do is we are making use of these features, and there are some weights which are defined. These are like multipliers for each of these features. So for this unit, the one in red, there is these set of multipliers. So W111 all the way up to, so if there are D such layers, so this was XD here, right? And what you'd have got was WD1. Okay, so this is a vector which corresponds to this neuron. So this neuron is going to make use of these weights. It's going to multiply this with the x's, that's the previous layer, and it's going to get some output. So some value z. Okay, so that is this part, the z part, and you apply some function, you will get another value here on the right side. So the
Ma'am,
final result is that output.
Yeah.
Yeah.
This weight is a constant or it will variable for the particular neuron?
So each neuron will have, it can have different weights. So nothing has to be constant.
No, ma'am.
Okay.
Means if we consider only one neuron, in
Mm-hmm,
the
mm-hmm,
one neuron for the
mm-hmm.
different training points, we have the constant value of the weighted. No? Means
Yes.
this
So this is,
W11
yes, this is a one weight for the entire network. Okay,
entire.
so yeah, so for if you get a new training point, so that will have a different value of x1 to xd, but these weights will be the same. Okay, so like in Perceptron also, right? What did we do in Perceptron? We had a single weight, right? There was a single vector, but if you got a new training point, what would change was this W transpose X. This is where the effect of the training point comes. But this W is the same. What you're assuming is that's your model. Okay, so that is going to be the same always. What changes for a training point is this W transpose X, that product. So similar thing even for neural networks. This W
Yes,
is
ma'am.
one,
Ma'am,
that's your model. Okay, Rishabh?
ma'am. Yes, ma'am. Ma'am, I got it that. Means I want to know that the why if we take the layer one, in that if we
Mm-hmm.
take two neuron, in the
Mm-hmm.
both the two neuron, why the weights are different?
Yeah.
Because
So,
if the weights are not different, then value will be same always, no?
yeah, if the weights are not different, exactly, the value will be the same. So there is no effect of adding one more. I mean, these weights will be redundant. Okay, if
Yes, ma'am.
you,
Ma'am, either there is some means activation function is changed or something means
yeah,
one neuron have the different activation function and second neuron have the different activation function, or we will change the b value or something, so that every different neuron will give the different value
yeah.
in
So
the
something
particular.
has to be different. So more generally, the way you write it is you, these can have different weights. Okay, and even it can have different weights, it can have different activations. There's a lot of possibilities here. So different W's, different B's, like between different neurons. And also, yes, you can, this one can be H1. And for this one, maybe you can use some other function H2. That's also possible. Okay. So there's nothing, there's no gold standard as such for what these weights or which things would be the same and all that. So if you have like different kind of weights, different kind of activation functions, it's going to capture a richer set of functions, right? Finally, what you get, there'll be a different function. There'll be a possibility for having different different kinds of functions. Okay. Rishabh, is it
Yes,
fine?
ma'am. Ma'am, and one more question means
Yes.
according to question means we need to specify how many layer we required, so how we will get that?
Yeah. So that's again, so this is exactly what we were talking of yesterday, right? These hyperparameters,
Okay,
right?
ma'am.
So this is something which is tunable. You have to try different values of this L. So in general, there are about L layers. So these layer 1 to L, these are called the hidden layers. Okay. Because that is something that you don't observe in your training. In your training, what is going to happen is this part, the x1 to xd or this layer 0, this will be your input. This will be observed. Okay, so this will come from your training data. And similarly, this last layer, layer L plus 1, this is the output layer. So that will be your wise. If it's a classification problem, maybe it's like 10 classes and one of them is the correct class for a training instance. That will be observed. Okay, so everything in between layers 1 to L, these are going to be hidden. And there is, again, there are a lot of parameters to choose. So one is the number of layers themselves, L. Then also how many neurons do you want in each layer, right? So more generally what you're going to have is layer, if there is a layer L, you will have something like NL. So that is the number of neurons. Okay, it could be that the first layer had maybe maybe two neurons, second one had five, third had three, something. All you can have different kind of configurations like this. So these are all tunable, right? So these are some things that you experiment with and try to find what is the best number for each layer. Okay. um,
Okay, ma'am.
right. Okay.
Excuse me, ma'am.
Yes.
Ma'am, here X1 will contain the first feature of all the training points.
uh,
Neuron X1.
so what we are writing here is a general model. So x1 is just used to denote the first feature value. Now, yes, if you are going to, so this is actually just a single number. X1 is just a real number. So what we are writing here is just for a single instance, for a single training point. You have an X and a Y. Then what is your neural network? What is the model? So that's the way in which it's written. But now when you plug in a different training point, you will use a different value of X. So X1 will be corresponding to that next training point that you use. It works that way.
Okay.
Okay. So yeah. So these are all like good questions because you should ask because there's a lot of scope for confusion just by the notations itself. So please ask whatever questions, whatever anything that's confusing, please ask. Okay. All right. Okay. So uh, can you just type maybe that whether it's clear or whether there are more confusions, whether or what's going on? It's clear. Okay. All right. All right. Fine. Okay. Cool. So yeah. So this is the underlying model for the neural network. Now, like I told you, like every machine learning model, there'll be some kind of a loss function that you're trying to optimize over. Now, if we are looking at classification, so neural networks, you can use it for classification. You can also use it for regression. Okay, so let's just look at the case where you use it for classification. What happens is, the output layer. So let's take the case where you have there are L hidden layers. Okay, and there is a layer n plus 1. So L plus 1 is the output layer. Okay, so what this is going to have is, like I said, these values a1, L plus 1, a1 to a10. Okay, so if there are 10 classes, what this is going to, you want this to be equal to the value you get. So y1 to y10. Okay, so let's just see what this would mean. So in your training instance, what you will have is a vector x. So this is like d-dimensional. And you will have one class, right? So something like whether it belongs to class 1. Okay, so how we will write this as, so let's just say that this is like class, maybe like class I. Okay, so this is the kind of data that you will get. Okay, so what you will, for our purposes, what we are going to do is we will write this as another vector. So something like this, y1 up to, so if there are 10 classes, so something like this, we will write a vector like this, y1 to y10. So y1 to y10. And what will happen is there is a yi here. And this yi will take a value 1. All these others will take a value 0. Okay. So this denotes that this instance is in class I. Okay. So that is one way to represent whatever data you're getting. Right. So data sets are given in different ways, but one thing you could do is you can transform it to have the output vector like this. So this is like the class vector. Okay, and so this is finally what you will see in the neural network. Okay, so the loss that you could have, right? So remember, like in this kind of modeling, the way in which we are writing a neural network, similarly this a1 to a10 is going to depend on the previous layer. So layer L, there will be a, like some values here, right? So a1L all the way up to maybe some a, so something like a15L, something like this. Okay, and what you will write is you can write a1 L plus 1 in terms of all these 15, right? And so on up to a10L, L plus 1, you can write it in terms of all these 15, this layer, right? So finally, what you're going to, the loss function that you're going to minimize, okay, what you're interested in minimizing is the output layer. So what you have is, so what did I write is AI, right? So AI L plus 1, or let me just call it AJ L plus 1. minus the actual value. So yj is the class vector that's given to you. So this is one point. Okay, so x and y. So this is what is given to you finally, x and y. And what you're trying to minimize is this difference. Okay, so AJL plus 1 depending on what kind of function. So if you're going to use the sigmoid function, you're going to get some values between 0 and 1. So this will be between 0 and 1. You want to see how close this is to yj. So you can take the square difference, and this you want to minimize, and you want this to be you want to take every point. So every of these neurons, so for every class whatever this value you got, you want to minimize this. Okay, and you want to do this for every training instance. So every xy in your data set, in your training instance, you want to compute this value. So this is the loss. So if this value is low, that means somehow the w's that you have fixed, the w's and the b's, right? So this is a function. This ajl is a function. It's a function of the w, the b, and of course your x also. So whatever you're getting is, if this value, if this difference is very low, if this overall term is very low, that means the w and b's that you have chosen is a good value. But if this is large, that means it's not a very good value and you have to do something. Okay, so this is so generally we'll write this as jwb, and of course it's also a function of your data. Okay, so sometimes people omit this detrain because that's kind of understood. So we'll also kind of use this, interchangeably. So JWB is defined in this way. Okay, and what you want to do finally is you want to minimize JWB. So the parameters of your network are W and B. So you want to find the W's and the B's which minimizes this JWB. Okay, so this is the underlying problem that you want to solve. Okay, now yeah, so
Excuse me, ma'am.
yes, Rishabh.
Ma'am, here in the loss function, ma'am,
Yes.
it is written that the a of j minus y of j. I think it should be a of the x and y of the x, I think.
So this one AJL plus 1, this is going to also, of course, this is going to be a function of W, B and X also. So there it's going to depend on X. Okay,
And
so
for the single point means for the, okay, ma'am, I got it.
right, yeah, of course, what you say is right. This is a function of X. Actually, this is true. This is going to be a function of X. Okay, but I'm just not writing this here, for the sake of, otherwise it becomes very cluttered. But of course, like for a different training point, this AJs are going to be different. So now for training instance, so if I call this x1 and y1, okay, so this is like training point 1. This is the first training point. Okay, so here what I'm going to get is one set of AJs. So A1 L plus 1 up to A10 L plus 1. This is what is going to happen. Okay, for this will correspond to this point. Now if I take x2, y2, so this is the next training point. So here I'm going to get some other one. So something like maybe so A1 L plus 1 up to A tilde L plus 1. This is going to be different. So these two will not be the same, right? So it's just, I don't have space to write one more index here. So that's the reason why I've just written it this way. Okay. So again, this y also, this y is going to correspond to this xy, this training point. Okay. So this is what you want to finally minimize. This loss is what you're interested to minimize. Now, just to remind you, like, okay, so there are different optimization algorithms which do this. So one method is what is called gradient descent. Okay, so we saw a version of this when we did approximate Q-learning. When we talked of regression, I told you about gradient descent. So what it is doing is, you have a function. Okay, so let me just take a, three-dimensional one. So I think that was somewhere here. Yeah, I just wanted to illustrate this. So maybe you have a function like this. So here what they're showing is there's a V1 axis and a V2 axis. Okay, and the function is in these two. I mean, so it's a function of V1 and V2. and it has something like a bowl shape. Okay, and now you are at some point here, so somewhere depending on this, green is the value that you get. So if you project it onto v1 and v2, that's where you are currently. Now you want to go, you want to make a step along some direction, and you want to get to the minimum. So the minimum point is somewhere here. Okay, and you want to get there. So the way you do it is you try to make some small steps. Okay, and which direction should you go? Okay, so that is typically a choice that is made by several algorithms. So one choice is to move in the direction of the negative gradient. Okay, so generally what so the algorithm goes like this. You initially start off with some random W and B's. So I'm sorry, I again exceeded the time. So I'll just tell you this gradient descent algorithm and then stop. We'll continue in the next class. So what you do is you randomly start off with some W and B. So you start off with, you randomly choose a W and B initially. Now what you do is you keep looping. You try to find a better value of W. So these are your initial Ws. Then what you do is you're at some time step. So you are initially starting off with W naught. So what you do in the next time step is you take this W naught, and what you do is you compute the gradient of this loss. This is the one that you're trying to minimize. So you find the gradient with respect to W. Okay, so and so this is actually a step in the direction of negative gradient. So it's a negative gradient you take, and you try to follow this direction. And sometimes there is also like how far do you want to go. For example, like if you remember, like this was kind of a function that we saw. Okay, this was an example that I again showed earlier. So you are at this point. Okay, you're starting off here. So maybe this is your W naught. Okay, and this is the value you got. Now you decided that the gradient is along this direction. Okay, so you're going towards the right. Now whether you want to take a small step or whether you want to take a large step, right? So that is also a choice that you can make. So this is written as some value alpha. Let me just call it as eta. Okay, so this is the direction in which you go. So which direction you go, that is the gradient. So the negative gradient actually. Okay, because you're trying to minimize the function, then you take the step in the direction of negative gradient. Because from your calculus class, probably you remember that the gradient is the direction of increase of the function. So you try to take a step in the negative gradient, and how much you go is given by this value eta. So this is called the step size. Okay, so this you do, and similarly, so for B also you do this. So B1 also you start off with your value B naught, and then you take the gradient in the direction of B. Okay, so the gradient with respect to B you take the negative direction, and then you increment this. Okay, so now you keep on doing this. Now you got a new W and B. So this gradient is also going to be, it will depend on these W's that you give. Whatever you feed it here, it's going to depend on that. So of course, when you evaluate this gradient, you evaluate it at a particular W naught, whatever you started off with. Now you repeat this till it converges. So till convergence, you keep doing this. So more generally, what you are going to have is you're going to have WT, and this is at time t plus 1, you're going to do this. Okay, so you keep doing this till convergence. What convergence means is, if there is, so as long as, between WT plus 1 and WT, the difference is, less than some very small value, some small epsilon, and maybe even BT plus 1. So BT plus 1 is a number. So even, both these, as long as both these happen, till this happens, till both these happen, you keep looping. And once you have that, that you're not making much progress, then you stop. Okay, so this is the gradient descent algorithm. So it has some guarantees for certain types of functions. Okay, so we're not going into that. So this is the most common algorithm that's used. Now it can take time, like depending on the size of, how big your W is. So we will see an example of how big this can be for the case of neural networks. So there are different variants that we use. So one variant is what is called the stochastic gradient descent. So maybe I will do this in the next class. So what neural networks typically use is the stochastic gradient algorithm. And to make it more efficient, what is used is the back propagation algorithm. So these are things that we will see in tomorrow's class. Okay. So I'll stop here for today. And if there are any questions, I'll hang back. Otherwise, we'll meet tomorrow. Right? Yeah. Thanks.